Greetings to all. Welcome you all for the presentation on Introduction to Composite Materials. Coming to the composite materials, it is one of the most advanced type of materials which we use nowadays in many engineering applications. So in this regard, I have taken this topic which is very quite interesting as well as need of the day, and nowadays we are using these kind of materials to in every engineering application, which is replacing most of our monolithic and conventional alloys. These are all composite materials or macroscopic combination of two or more distinct materials which have a discrete and a recognizable interface separating them. This is what the ASM handbook says. See, basically composites are the heterogeneous combinations, heterogeneous mixture of two or more different materials, whereas alloys is another similar kind of content where it is a microscopic combination of two or more elements. So because of that reason, it is like a mixture what we are getting in case of alloys. These are all solid solutions with most of the things are a homogeneous kind of mixture. That's the major difference between composite materials. Here we have a clearly recognizable interface, physically and chemically distinguishable interface which exists between the two or more materials, which are the ingredients of this composite materials. Coming to the characteristics of composite materials, these are all macroscopic combinations with two or more distinct materials having a discrete and a recognizable interface separating them. These composites, thus as I mentioned already, these are all heterogeneous mixture which are naturally occurring. The most common is wood, which is a natural composite where there is a mixture of lignin as well as cellulose. So here, as I am saying, there are two different types of constituents which are interface exists between these two types of phases. In that case, we call one phase as a matrix phase and the other one as a reinforcing phase. So reinforcing phase, here it is completely spreaded, which is being reinforced, or the materials which we call it as a reinforcements are being held together with the help of a matrix material. The reinforcing material may be in the form of fibers, particles, or flakes, different types. Generally, commonly used types of reinforcement materials are in the form of exist in the form of fibers, particles, and flakes. The matrix phase, which are generally continuous, which helps to hold these different dispersed phases of reinforcement materials together, and at the same time it transfers the load among them. In detail, we are going ahead in the next slide. Coming to the examples, examples of composite systems includes like day-to-day which we come across with is one of the most concrete, in which the steel fibers or steel rods are reinforced into the cement, epoxy reinforced with graphite or graphite fibers or carbon fibers or glass fibers, which we use it in many engineering applications, including the aerospace applications to the windmill blades. Composites are very strong, stiff, and very light in weight. So ratios of strength to weight ratio or stiffness to weight ratio, which we generally call it by the name called a specific weight or specific density or a specific strength, a specific modulus. These are all several times greater compared to the steel and aluminium. These are one of the few important characteristics or notable characteristics of composite materials. Coming to the next, role of reinforcements. In the role of reinforcements, the major roles are like four important roles which I have listed out here. Wow, the first one being the strength to composite material is mainly imparted by the reinforcement, because the matrix material does not possess the required strength, which is being imparted when we add the particles or fibers or flakes to the basic matrix material. So because of that reason, the major function of reinforcement while we are selecting, we should select such a way that it is contributing towards improving or enhancing the total strength of the composite material. They serve additional purpose of heat resistance on conduction, resistance to corrosion, and provides rigidity. See here mainly, like as I mentioned already, there are two different materials, each are having their own specific characteristics. When I want to tailor it, when I want to combine the two or more properties, we are going for the composite materials. In the same way, here when in this regard, like in the composites, where the reinforcements, if I want to improve the enhance the heat resistance of the total composite material, then the reinforcement is selected such a way that I want to increase the heat resistance on conduction. So reinforcement that embellishes the matrix, which must be stronger and stiffer than the matrix and capable of changing the failure mechanism of composite. Let us take an example such a like a matrix. If it is of a highly ductile material, like example in the metal matrix composites, those are base alloy like aluminum, those are all highly ductile in nature. If I want to change the ductile failure of this aluminum alloy into the semi ductile nature, then generally we go with the reinforcements which can be added or reinforced into the aluminum alloy. It may be in the form of fibers or particles, which changes the failure mechanism of the whole composite material or the resultant composite material. In the same way, the contribution towards the properties such as a coefficient of thermal expansion, conductivity, those are highly remarkable. So these are some of the few major important role of reinforcement. Similarly, when I could take the case of matrix, even it has its own role to play in the composite. Mainly it is, as I mentioned, it is going to hold the fibers, hold the reinforcement particles together. That's why it gives the required shape to the whole composite itself, and to keep the fibers in place or to keep the particles in place. And it helps to transfer the stresses among the fibers, so that the whole load which is applied on the resultant composite material on the part of that composite material is being nearly uniformly distributed among the fibers or the reinforcement particles. To protect the reinforcement from the environment, like chemical and moisture kind of thing, and to protect the surface of the fibers from mechanical degradation, UV degradation, and also it acts like a shielding from damage due to mishandling or any handling sources during its service. Coming to the next, about the advantages of composites. Major advantages being the high resistance of fatigue and corrosion degradation, high strength to or stiffness to weight ratio. That is what I said, high specific strength or high specific modulus. These are some of the important advantage of composites compared to the monolithic alloys. That's why most of engineering applications nowadays, especially advanced engineering applications, are aiming towards replacing the monolithic conventional alloys with the composite materials. Due to the greater reliability, there are few inspections and structural repairs, because composites can be manufactured to the near net shape components. That's why there is a very greater reliability and very inspection and structural repairs we can observe. Directional tailoring capabilities is one of the important characteristic here. Like example, if I want to increase the strength in the transverse direction, then we can achieve it if it is in one particular direction. Like in the case of fibers, for fiber unidirectional fiber reinforced composites, where we can concentrate on only directional oriented properties also, which helps to meet the design requirements in many engineering applications. Coming next is about the improved dent resistance, which is normally achieved. Composites offer improved torsional stiffness, high resistance to impact damage, and they are dimensionally stable. They have low thermal conductivity, and low coefficient of thermal expansion also. Manufacturing and assembly are simplified because of part integration. As I mentioned, most of the components which are manufactured with the help of composites are near net manufacturing. Because of that, even the manufacturing cost and other costs also get reduced. Associated costs will get reduced. The improved weatherability of the composites is one of the major advantage in marine environment, as well as the corrosion resistance, which improves the durability and reduces the downtime for maintenance. Close tolerances can be achieved without going for machining. Like secondary machining operations are being reduced here. It is highly, I do agree that there are. It is very impossible to eliminate the all secondary operations, but at the same time we have the chance to reduce the secondary operations when we select the composite materials as alternative material for the regular conventionally using materials like alloys. Next is about the disadvantages. Similar to the advantages, even we have some disadvantages of the composite materials in engineering applications, because as I said, we are aiming towards replacing the monolithic alloys with the composites, but in some applications it is highly impossible, or it is it is possible in the future to replace to replace the alloys with the composites. Yeah, with the limited property, with the characteristics, with some limited applications there, because of disadvantages or limitations of composites. High cost of raw materials and fabrications. Composites are more brittle than the wrought alloys or wrought metals, and there's are more because of that they are more easily damaged. Transverse property, if I am like example, as I mentioned already, unidirectional properties, if I want to improve, then we go with the unidirectional fiber reinforced composites. But in that case, when I am concentrating on the longitudinal properties, the transverse properties may become weak. And matrix so in that case the transverse properties may become weak, and if I want to apply the load in the transfer direction, the composites may get fail in easily. Matrix is weaker compared to the reinforcements, therefore it have possess some low toughness. Reuse and disposable may become difficult, because like example, in the polymer composites, polymers are very difficult to separate and dispose. Those are all some of the challenges with respect to the disposal issues of the composites, and it is very difficult to attach. It is very difficult to just like in the alloys we are going for welding, but in the same way, if I am going with the composites, it is very difficult to attach. And repair introduces repairing of the composite material components introduces new some new problems, like it is limited because of some reasons, like materials require refrigerated transport and storage and have limited shell life. And hot curing is necessary in most of the polymer composite cases, requiring special tooling. Hot or cold curing takes time. Analysis is also bit difficult. As I mentioned, it is a heterogeneous combination. It is not a homogeneous combination, that makes it the analysis of these materials difficult. Based next we go ahead with the what are the classifications of composite materials. Based on the matrix material, we are classifying the composite materials as polymer matrix composites, metal matrix composites, and ceramic matrix composites. Based on the reinforcement materials, we are classifying them as fiber reinforced composites, particle reinforced composites, viscous reinforced composites, and laminated reinforced composites. Beyond that, we have this natural composites and all such special cases. Those are all a special category of composite materials. But since either the matrix or the reinforcement is of falls under one of these categories, that's why we can classify them under the same. Polymer composites. Polymer makes ideal material in most of the cases because they can be easily processed, also possess a very lightweight and desirable mechanical properties. It follows therefore the high temperature resins are extensively used in aeronautical applications, just like phenolic based resins. Two main kind of polymers which we can classify them as or we use it as a matrix material in composites are thermosets and thermoplasts. Thermosets have very good qualities such as well bonded three-dimensional molecular structure after curing. They decompose instead of melting on a hardening, merely changing the basic composition of the resin, which is enough to alter the conditions suitable for curing and determine its other characteristics. They can be retained in a particular partially cured conditions to over a prolonged time of a prolonged period of time, rendering because like example we can store it like a pre-impregnation stage itself, and we can store it under refrigerated conditions, and whenever we want it as a component, we can use it as a laminar layer, and we can make it as a laminated composites. Thermosets are very feasible, flexible, thus they are most suited as matrix bases for advanced conditions, fiber reinforced composites also. Some of the examples for thermoset polymers are epoxy, vinyl ester, polyester, and phenolic resins. Thermoplast composites have one or two dimensional molecular structure. They tend to at an elevated temperature and show exaggerated melting points. The point Tg becomes very critical here. Another advantage is that the process of softening at elevated temperatures can reverse to regain its properties during cooling. Resins reinforced with the thermoplastics now comprised an emerging group of composites. They are emerging nowadays. Earlier the thermoset was the major reinforcing polymer matrix materials which was being widely used. Nowadays even the thermoplasts are being emerged in various engineering applications as a matrix material for composites. In crystalline thermoplastics, the reinforcement affects the morphology to a considerable extent, prompting the reinforcement to empower nucleation. Whenever the crystalline or amorphous, these resins possess the facility to alter the creep over an extensive range of temperature. But this range includes the point at which the usage of resins is constrained and the reinforcement in such systems can increase the failure load as well as creep resistance. Some of the examples for thermoplastic matrix materials includes LDPE, low density polyethylene, UHMP, ultra high molecular weight polyethylene, and PET polyethylene. There are many more. Like PS or PEK, there are many more. These are this is about the thermoplastic matrix. Next, moving ahead to the metal matrix composites. Metal matrix composites are present, though generating a wide interest in research fraternity, are not widely used as a plastic counterparts. Their high strength, fracture toughness, and stiffness are offered by metal matrices than those offered by polymer counterparts. They can withstand elevated temperature. That is one of their major advantage even in the corrosive environment compared to the polymer composites, because polymers generally degrade at a higher temperature, whereas metals can sustain at that temperature. But the temperature is limited up to the melting point of the matrix material or a alloy matrix alloy. Most metals and alloys can be used as a matrices as they require reinforcement materials which need to be stable over a range of temperature and not reactive to. However, the guiding aspect for the choice depends especially on the matrix material. Light metals forms the matrix for temperature applications, and the reinforcement in addition to the aforementioned reasons are characterized by the high moduli. Most metals and alloys have can make a good matrix. However, practically the choices for low temperature applications are not many. The major characteristic for metals to use it as a matrix material is generally their density. The general lightweight metals or light metals are responsive, and their low density provides an advantage. That's why only the low density metals or alloys are used as matrices in engineering applications. Titanium, aluminum, and magnesium are very popular matrix materials. Among them, aluminum takes a major percentage of role, or a major percentage. It takes the major percentage among all the composite matrix of MMCs. Currently it is in vogue, which are particularly useful for aircraft applications. If metallic matrix materials have to offer high strength, they require high modulus reinforcement. The specific strength or strength to weight ratio of resulting composites can be higher than most alloys. That's the major reason why the MMCs are preferred over monolithic alloys. The melting point, physical and mechanical properties of the composites at various temperatures determine the service temperature of the composites. Most metals, ceramics, and compounds can be used with matrices of low melting point alloys. Coming to the next category of composite materials, that is ceramic matrix composites. Ceramic matrix composites are category of composite materials in which the ceramics are being used as a matrix material. They exhibit very strong ionic bonding in general, and few cases covalent bonding, high melting point, good corrosion resistance, stability at elevated temperatures, and high compressive strength. render ceramic based matrix material a favorite for applications requiring a structural material that does not give away at temperature above 1500 degrees Celsius. Since here the matrix material itself is a ceramic which possesses a very high melting point, because of that reason they are can be used, or they find their applications in very high temperatures or at elevated temperatures, even when there is a above 1500 degrees Celsius, where the metals or polymers are difficult to use as a materials, where we can use the CMCs. High modulus of elasticity and low tensile strain, which most ceramics possess, have combined to cause the failure of attempts to add reinforcement to obtain strength improvement. The one of the major limitation of the CMCs is the matrix are very brittle in nature. That's why when we add the fibers, as I mentioned in the characteristics of the composites, the strength or the changing the failure mechanism can be connected here, where the CMCs, where brittle failure is going to occur, that is ceramic matrix having a brittle failure mechanism, which can be converted, which can be transformed from the brittle failure into the semi-ductile failure or nearly ductile failure. So the or we can bring it down, we can improve the ductility of that material, not completely very brittle. So that is the reason we by that way we can use these CMCs as a structural materials. This is because at the stress levels at which the ceramics ruptures, there is insufficient elongation of the matrix, which keeps the composite from transferring the effective quantum of load to the reinforcement, and composite may fail under the percentage of fiber volume is high enough. So material is reinforcement, like ceramics material is reinforcement to utilize a high tensile strength of the fiber to produce an increase in load bearing capacity of the matrix. And also in addition, a high strength fiber to the weaker ceramic has not always been successful, because of the resultant composite have proved to be weaker. The use of reinforcement with high modulus of elasticity take care of this problem to some extent, and at the same time presents pre-stressing of the fiber in ceramic matrix is being increasingly resorted to as an option. When ceramics have a high thermal expansion coefficient than the reinforcement materials, the resultant composite is unlikely to have a superior level of strength. In that case, the composite will develop strength within the ceramic at the time of cooling, resulting in micro cracks extending from fiber to fiber within the matrix. So that's about the categorization of composites based on the matrix material. Now we are moving ahead the categorization of composites based on the reinforcement types. First one is in that category is fiber reinforced composites. When we are adding the reinforcement in the form of a fibers or a very long fibers, they are then we call it as a fiber reinforced composites. They are important class of reinforcements because they satisfy the desired conditions in most of the cases and transfer the strength to the matrix, constituent influencing the and enhancing the properties as expected or desired. The performance of the fiber composites is judged by its length, shape, orientation, composition of the fibers, and mechanical properties of the matrix. The length of the fibers, shape, orientation, as well as the composition plays a very vital role on the resultant composite material properties, especially like orientation, sometimes random orientation, sometimes it may be unidirectional, bidirectional, and again 0 degree 45 degree kind of combination, 0 degree 90 degree combination of plus 45 minus 45. These are different orientations by which we are reinforcing the fibers into the matrix material. The orientation of the fibers in the matrix is an indication of the strength of the composite, and the strength is greater along the longitudinal direction of the fibers. This matters a lot when we are going for the unidirectional fiber reinforced composites. Monolayer tapes consisting of continuous or discontinuous fibers can be oriented directionally, stacked into piles containing layers of filaments also oriented in the same direction. Orientation of short fibers by different methods is also possible, like random orientation by sprinkling onto the given plane, or addition of matrix in liquid or solid state before or after deposition. Next category in this is the laminated composites. As I said, like impregnated laminates are being stored, and whenever we want the composite parts, those impregnated laminars can be laid one over the other, and we can prepare the laminated composites. So these are all found in many combinations as number of materials. They can be described as material comprising of layers of material. As a laminate, the name itself suggests that it is a stack of laminas or layers. So material comprising of layers of materials which are bonded together, we call them as laminated composites. The structural applications of the composites are mostly obtained in the form of laminates. They provide the inherent flexibility that a designer exploits to choose the right combination of material and directional properties for an optimum design. A lamina is the basic building block in the laminate. A lamina may be made from a single material, metal, polymer, or ceramic. Generally, the polymer composites are popular among them from a composite material. A composite lamina, which all filaments are aligned along one direction parallel to each other, is called unidirectional lamina. Various such hybrid laminates can be prepared, where, like example, if I want a composite with a hybrid of glass fiber reinforced composites and carbon fiber reinforced composites, or aramid fiber reinforced composites, one layer we can make it with the impregnated fiber with glass fiber, and another impregnated lamina with carbon fiber. So in that we can combine them, we can obtain the hybrid composites, which is possible here. For most of the practical applications, choosing various combinations of layers of metallic materials, polymer composites, metal matter composites, and ceramic composites. Aramid epoxy composites are commonly combined with carbon epoxy composite to make the carbon Kevlar hybrid composites, to obtain a cost effective composite with superior compressive and impact resistance, because aramid possesses a very good impact strength, whereas carbon fiber possesses a very good compressive strength. And at the same time, the total cost reduce when we are, because carbon fibers are most costlier compared to the aramid. So we can reduce the cost, we can obtain a superior characteristics by combining two or more different fibers. So that is possible with the help of laminated composites. Kevlar fibers are inexpensive as compared to carbon fibers, and effective in resisting the impact force. Carbon fibers in turn improves the compressive strength and makes the carbon Kevlar hybridization as most popular among the polymer composites for the structural applications. Coming to the next category here, particular reinforced composites. Particulate or particular form of reinforcements, particulate reinforcements are popular in various applications, especially among the metal matrix composites and ceramics composites. Here the reinforcements are added in the form of a particulates or particles of one particular phase, it may be inorganic particles, or some compounds are added in the form of particles, which are known as particle reinforced composites. In particulate reinforced composites, particles strengthen the system by hydrostatic cohesion of fillers in matrices and by their hardness relative to the matrix. Three-dimensional reinforcements in composites offer isotropic properties compared to the fiber systematically orthographic planes. Here, like when I'm comparing it with the unidirectional fiber reinforced composites, where it is not possible to obtain the isotropic, which is possible here when we are adding the particulate into the matrix alloy or ceramic matrix, where we can achieve nearly equal or nearly uniform isotropic. It is very difficult to say like highly isotropic, but or it is not possible also, but at the same time nearly isotropic kind of properties is possible when we go with the particulate reinforced composite. Since the particles are dispersed or distributed throughout the volume of the matrix, to some extent we can achieve it. Since it is a homogeneous, the material properties require sensitivity to the constituent properties as well as the interfacial properties and geometric shapes of the array. The composite strength usually depends on the diameter of the particles, interparticulate spacing, and volume fraction of the reinforcement. The matrix properties influences the behavior of particulate composites too. because based on their strength, based on their density, so that is of the alloy, so it contributes to it contributes to partially to the resultant properties of the composite, and the other part is being contributed by the reinforcement particulates. Next category is about the viscous reinforced composites. Single crystal grown with nearly zero defects are termed as viscous. They are generally discontinuous and short fibers of different cross sections made from several materials like graphite, silicon carbide, copper, iron, and many more. Typical lengths are in the range of the 3 to 55 nanometer range. The viscous, it differs from the particles in that case. That is based on the length and the size. Viscous have a definite length to weight ratio greater than the one, and they have an extraordinary strength up to 7,000 megapascals. Researchers have shown that viscous strength varies inversely with the effective diameter. That's about the classification of composite materials. Next, we go ahead with the applications of the composite materials. Coming to the first category, aircraft or military applications, commercial, pleasure, and military aircrafts, including the components for aerospace and related applications. It goes from the structural materials to the bearing applications for like using metal matrix composites as bearing applications, fuselages, many more, including the cone structures, many more applications we are using in the aircraft and military components. Coming to the next one is about the appliances of business, composite applications for the household and office, including appliances, power tools, business equipments, some automotive, largest of the markets. Products include parts for automobiles, trucks, rails, and farming applications like bumpers, the doors, the inner components are like interior components of the automobiles, and alloy wheels. There are many more such components which we use it as a part of automotives. Next is about the civil infrastructure. Nowadays, most of our civil architectural applications includes the composites. It may be with respect to the shape, architectural shape, compared, and also like different structures of the buildings, like bathroom fittings, and also when I go with the broader sense, like various civil infrastructure applications, which includes the buildings and railroads, bridges. Those are all nowadays used with the composites. The basic is without concrete we are not going ahead with the most of our building materials. So concrete is one best example for the composite, and it finds applications in all civil and infrastructure. Yeah, there are few cases where we can find the polymer composite structures in the architectural applications too. Construction applications includes the materials for homes, offices, architectural applications. It includes the swimming pools, bathroom fixtures, as I mentioned already, and well panels, roofings, and architectural claddings, domes. So these are all some to list out. Next is about the consumers. The consumer goods, which includes the sports and recreational equipment such as golf clubs, tennis rackets, snowmobiles, mobile campers, furnitures, microwave cookwares. So there are many more. Basically, like golf clubs, where the head has to be of a higher weight, where the pole has to be of lower weight or low density, or tennis rackets and badminton rackets. Those all generally nowadays made with the graphite or carbon fiber reinforced composites. Corrosion resistant equipments, especially chemical tanks, or tanks we use it in water filters, many chemical processing industries, pulp and paper oil industry, pulp and paper industries, oil and gas industries, water and waste treatment markets, fans, gratings, pumps, hoods. These are some of the components which are used as in the industries as a corrosion resistant equipments. The major part is being like the polymer composites are inherent to the corrosion. They are not they are corrosion resistant materials. That's why they are widely used for these kind of applications. Even sometimes we go with the ceramic based too. Electrical equipments, the encompassing market includes the components for both electrical and electronic equipments. It starts from the printed circuit boards up to the pole line hardware, substation equipments, microwave antennas, printed writing boards, and even nowadays, like street light poles are being manufactured with the help of polymer composites too. Coming to the other one, the important category of engineering application, which is marine, where products for commercial, pleasure, and naval boats and ships, boat hulls, boat structures, because under the marine environment, where the components are exposed to the saline environment or a corrosive environment, polymers are in resistant to those kind of corrosion nature, corrosion environment. So because of that, they find their applications in the marine too. Even the submarine structures are being made with the polymer composites. So these are thank you for this watching this video. These are the references which I used for preparing this presentation. Thank you all.